Hello mathematicians. Today next we see one very nice problem from real analysis, and you see same problem with a little modification, like one time it is asked sin x, other time it is asked cos x. This is 2014 June, this is 2015 December, and options are exactly the same. Okay, so that is why you should prepare the previous year questions. Okay, so and the argument is pretty much exactly same for both the sin x and the cos x. Okay, let's see why is it so, and let me phrase the question. F from 0 comma 1 to r be a continuous function. Suppose modulus of f of x minus f of y less than or equal to mod sin x minus sin y. So in this problem it is given mod cos x minus cos y. Okay, then f is discontinuous at least one point in open 0 comma 1. F is continuous everywhere on open 0 comma 1 but not uniform. F is uniformly continuous. Limit extends to 0 plus f of x exists. That is a right limit at the point 0 exists. Okay, so let's see how to approach this problem. So now we need a very important concept called Lipschits continuous functions. Okay, there is more general thing called Lipschits functions of order alpha, that we will talk about it in a different video. So here basically you have one. So that this Lipschits continuous functions are Lipschits functions of order one, and more general, usually you will have an alpha here, that is called Lipschitz functions of order alpha. Anyway, for this function we just confine ourselves to Lipschitz continuous function. A function f from open a comma b to r is said to be Lipschitz continuous if you can find a k greater than or equal to 0 such that modulus of f of x minus f of y less than or equal to k times mod x minus y for all x comma y in the interval a comma b. Okay, so suppose we have a Lipschitz condition, Lipschitz continuous function. We claim that Lipschitz continuous functions are uniformly continuous. So in particular, Lipschitz continuous functions, if a function satisfies this condition, it is called a Lipschitz continuous because it will be continuous first place and it will be uniformly continuous also. Okay, let's see why it is uniformly continuous. In the description I have given a link to a video in which I have explained the definition of continuous function and uniformly continuous functions very clearly with the examples. So if you want to understand the difference between continuous and uniformly continuous function and using through some examples, please check the video in the introduction, in the description. Okay, let's continue. So we claim that any function satisfying this condition is uniformly continuous. So we take, let epsilon greater than 0 be given. We take delta to be epsilon by k. Okay. Now suppose mod x minus y is less than delta, then mod f of x minus f of y will be from the given since f is Lipschitz, it satisfies this condition. Mod f of x minus f of y less than or equal k times mod x minus y. Since mod x minus y is less than delta, mod x minus y is less than delta and delta equal to epsilon by k. Okay, so mod f of x minus f of y less than or equal to k times mod x minus y, but mod x minus y is epsilon by k. So we conclude that mod f of x minus f of y less than k times epsilon by k, that is nothing but epsilon. So whenever mod x minus y less than delta, we get modulus of f of x minus f of y less than epsilon, and the delta depends only on epsilon. Therefore f is uniformly continuous. Okay, so here I am not explaining many things about uniformly continuous. You please check the video if you want to learn the basics of uniformly continuous very clearly. Okay, why this delta independent of x comma y means that it is uniformly continuous. Such things can be understood through that video. Okay, now we have proved that any function satisfying Lipschitz condition, Lipschitz continuity condition, is uniformly continuous. Next, we prove a similar result. See, all these results are very important. Lipschitz continuous functions are uniformly continuous. Next, we are going to prove that if a function, if a differentiable function has a bounded derivative, then it is Lipschitz continuous. Okay, so these results are sometimes asked in the interview also, like NBHM, TA for interview also. And these results you can use in many problems in real analysis. Okay, so let's see why a function has a bounded derivative is a Lipschitz continuous. So we assume suppose derivative is modulus of f prime of x less than or equal to k for every point in open a comma b. Now I take 2 points c less than d arbitrarily from the interval a comma b. Okay, so then this function f is continuous in the open a comma b. So if it is continuous in the open a comma b, now this closed interval c comma d is a subinterval of the open interval a comma b. Therefore, f is continuous on this closed interval. F is differentiable in open a comma b. Therefore, f is differentiable in the subinterval open c comma d. Sorry for the typo. Therefore, by mean value theorem, okay, so mean value theorem states that if you have a continuous function on closed C comma D and a differential function of open C comma D, then you can find Z belongs to the interval open C comma D such that f prime of Z equal to f of C minus f of D by C minus D. Okay, so we have modulus of f prime of Z equal to modulus of f of C minus f of D by C minus D. Okay, now this implies that modulus of f of c minus f of d equal to modulus of f prime of z times modulus of c minus d. But the modulus of f prime of z is less than or equal to k because z is a point in open c comma d means f is a point in open a comma b. But modulus of f prime of x less than or equal to k for every point in a comma b. Okay, good. So we conclude that modulus of f of c minus f of d less than or equal to k times mod c minus d. But c and d are arbitrary points in the interval a comma b. Therefore, we get modulus of f of x minus f of y less than or equal to k times mod x minus y. Okay. Here we observe that this k we are getting, this is called a Lipschitz constant. If f is a different bound, f has a bounded derivative, then the bound for the derivative, that value is the Lipschitz constant we are getting. Okay, that is one thing to observe. Now we come back to our problem. In our problem, we are given sin x, mod sin x. I mean, like somehow we want to use this mod sin x minus sin y. So we deal with sin x. So in the for this problem, you have to do same thing with cos x, but it is exactly 100% exactly same. So you can try it by yourself. Okay, so we consider f of x equal to sin x. Then modulus of f prime of x is modulus of cos x because derivative of sin x is cos x, and the modulus of cos x is less than or equal to 1. Okay, for all x belongs to open 0 comma 1. Therefore, sin x has bounded derivative. Therefore, sin x is Lipschitz continuous. Therefore, we get modulus of sin x sin minus sin y less than or equal to this Lipschitz constant is usually the bound for the derivative. Okay, so we just observe it here. So we get 1 times mod x minus y for all xy belongs to open 0 comma 1. Okay, now we come to our problem. In the problem, it is given that mod f of x minus f of y less than or equal to mod sin x minus sin y, but mod sin x minus sin y less than or equal to mod x minus y. That is what we proved. Therefore, mod f of x minus f of y less than or equal to mod x minus y. Therefore, the function f also Lipschitz continuous with Lipschitz constant here we have 1. Okay. Therefore, f itself, if a function f satisfies this condition, then since sin x is Lipschitz, f is also Lipschitz. Okay, so this much is enough to solve this problem. So since f is Lipschitz, it is uniformly continuous. Therefore, discontinuous is wrong. Just continuous but not uniform is wrong. F is uniformly continuous correct. If f is a uniformly continuous function open 0 comma 1, then it can be extended to a continuous function on close 0 comma 1. Okay, that is a necessary and sufficient condition. F is uniformly continuous on an open interval a comma b if and only if f can be extended to a continuous function on the closed interval, especially in the endpoints. Or equivalently, f is uniformly continuous on open a comma b if and only if the right limit at the point 0 exists and the left limit at the point 1 exists. Okay, see, if you look at the interval open 0 comma 1, you can approach 0 from this side only. In the interval open 0 comma 1, you can approach 1 through this direction only. Okay, so this is coming from right, so it is a right derivative. It is coming from left, therefore at a left, sorry, it is a right limit, it is left limit. So at the end of the interval, it at the end points of the interval, after the left point, you can find only right derivative. In the right end point, you can find only left derivative. So if it is uniformly continuous, then both exist. Okay, not just limit extends to 0 plus f of x, even limit extends to sorry, limit extends to 1 minus f of x also exist. Okay, that also you keep it in mind, if since f is uniformly continuous. Okay. Okay, so I hope you understand something new in this problem. If you like this video, please like and subscribe to my channel. Um, if you have some doubts, if you want me to do some particular problems in pure or applied mathematics, anything, just comment below. I'm very happy to do the problems. Thank you.